If water is acting as an acid, recall that water will definitely split to give us what? H plus and OH minus. So water acting as an acid can donate a proton here. Are you getting it? When it donates a proton, what are we now going to be having? You are going to be having NH4 plus, because you already have NH3 here plus 1 proton, making it what? 4. So here becomes NH4 positive. What do you think will be left with water? OH negative. So that water that donated the, now recall that in this case water is acting as an acid. Initially water acted as a base. Is that okay? So at the end of the day, this one comes here, we are going to have NH4 plus, and then here will become remaining what? OH minus. Now this OH minus is the conjugate base, which is very correct. Now why this one here is the conjugate acid. Is that okay? Now say in the reverse reaction, when we talk about the reverse reaction, we are talking about the backward reaction. This reaction from this one going to this way is called the forward reaction. Why this one coming back is called the what? The reverse reaction. So if you want to write it in such a way that this one is coming back to this place, it's called the reverse reaction. Why this one coming this way is called the forward reaction. So when we talk about the reverse reaction, it means we are looking at the reaction from this side down to this side. Are you getting it now? So in the reverse reaction, the hydrozonium ion act as a proton acceptor, which is this OH negative, act as a proton acceptor, and H4 ion act as a proton donor. Hence, it is the conjugate acid. Now, substances such as water, ions such as hydrogen sulfate ion are both brustoluric acid and bases. They are known as ampholites and shows amphiprotic behavior. So you may be asked, what are ampholites? Or substances that show amphiprotic behavior. They behave as acids. These substances, my dear students, behave as acid and also as base. Are you getting it? These substances, they behave as acid and also as base. Hence you call them amphiprotic. So amphiprotic substances are substances that behave as acid and also as what? As base. So that you call them amphiprotic, or you can call them what? Ampholites, as you can see here. An example of ampholite is water. I've told you before that water behave as acid and also as a base depending on the reaction. Is that okay? And also the hydrogen sulfate ion. Now if you look at this reaction, which is the acid, which is the base, which is the conjugate acid, and which is the conjugate base? Look at the reaction very well. Which is the acid, which is the base, which is the conjugate acid, which is the conjugate base? So the question is, which is the acid, which is the base, which is the conjugate acid, and which is the conjugate base? Now look at this reaction very well. You agree with me that if you look at this part of the reaction, which of them donated a proton? You agree with me that this HSO4 donated a proton. Look at it. This one donated a proton, right? To what? H2O. Now when it donated the proton to H2O, H2O became H3O plus. Why this one is now remaining what? SO4. Now this thing is written as SO4 minus. Are you hearing it? Now as a positive charge is leaving, one negative charge will become visible. What this reaction is all about is what I'm going to show to you here. You have something like this, and let me show you here, which is HSO4 negative plus H2O, right? To give us, now it's a very simple reaction, but you have to understand the process. HSO4 will give out positive charge, which is a proton, to H2O, and where that happens, what are you going to have? You are going to have this positive charge add with this H2O, going to give us H3O plus What will be left here? SO4. Recall that there's a positive charge leaving. Because a positive charge is leaving, listen, whenever one positive charge leaves, a negative charge becomes visible. So initially you're having one minus here, but this positive charge that is leaving will make the minuses or the negative sign here to be 2, the ions, or the negative ions. So here we are now going to have 2 minus. Is that okay? Is that okay? So this is what you are going to have. Now this whole thing here, listen, which of them is now the acid and which is the base? Because this one donated the proton to this is regarded as the acid, this is regarded as the base. But when you now come to this way, this is the conjugate acid and this is the conjugate base. Now the conjugate acid is the one at the product side that is capable of donating a proton. The one at the product side capable of donating a proton is called the conjugate acid. It's called the conjugate acid. So this H3O plus is the conjugate acid, while the SO4 2 minus is the conjugate base. Is that okay? Do you understand? Do you understand? Do you understand? Alright, so that is the differences between the acid-base reaction equilibrium. Now let's look at another example quickly. Now if you look at this reaction very well, it's more like the opposite of the first reaction. Look at it. This reaction says is the case where water is acting as the acid. This reaction is a case where water is acting as the acid. So you have HSO4 minus plus H2O. This reaction is reversible. Alright, is it? Think it should be, because we are talking about, yeah, it's reversible. Acid-base equilibrium. Now open, so that at the end of the day this one is acting as the acid. So if it is water is acting as the acid, it means it has to donate a proton here. Now when it donates a proton there, what are we now going to have? You are now having a positive side charge coming to H2SO4. So here will become H2SO4. Are you getting it? Because when this H plus add here, the positive will cancel this negative from here. H plus H will give us what? H2. We have H2SO4. Recall that this H2O is supposed to be OH negative and H plus. H plus don't come out. So what is left here is what? OH negative. Now the question now is, which of them is the acid and which is the base? That is the question. Which is the acid and which is the base? Now this one that donates a proton is the acid, while this one here is the base. Now whenever you now come to this side, this is the conjugate acid, while this is the conjugate base. Is that okay? It's very, very easy, just based on your understanding of fundamental concepts. Is that clear? So let's continue. Now let's see. Now we have an exercise here. For each of the following, identify the acid, the base, and the conjugate base, the conjugate acid and the conjugate base. Now the question now is, how do we identify them? It's very, very easy. Let's identify them one after the other. So I'm going to use this pen to identify them. Now come to this side. Which of them do you think donated a proton? Is it H2PO4 negative or HCl? Now if you look at this side, HCl is now left with what? Only Cl. So it means HCl donated to this. Now, if HCl donated to this proton, it means that HCl is the acid, while this is the base. Now, when you now come to this side, you know, I told you that the acid will now become the base here. So this one become the conjugate base, while this one become the what? Conjugate acid. Right? It's very easy. Now look at this one. Which of them is the acid and which of them is the base? Of course, you can see that phenol donated a proton to water to now form phenazide ion. This is phenazide ion, right? This, what you see here, this is H5OH, can also be written as this OH. So it donated a proton to H2O to form this plus H3O positive, which is hydrozonium ion. So phenol is the acid, while this is the base. Now here, this will become the conjugate base based on understanding, and this will become the conjugate acid. Are you getting it now? Now this is hydroxylamine, which is NH2OH with water. Now which of them do you think is the acid? Which of them donated the proton? You can see from this reaction that water donated the proton. So water will become the acid, while this becomes the base, right? Why, if you now come here, the acid will become the base. So here becomes conjugate base, right? Why this one becomes the what? The conjugate acid. Conjugate acid. Now the last one, this is ammonia and sulfuric acid. Which of them is the acid and which of them is the base? Of course, you know sulfuric acid, from what you can see here, is the one that donated a proton. Look at it very well. You agree with me that it was sulfuric acid that donated a proton here. So sulfuric acid, I mean the sulfate ion, not sulfuric acid, this sulfate ion is the acid, while ammonia is the base. Why here, this is the conjugate acid and this is the conjugate base. It's very easy, right? Exactly. So this is me explaining your entire material for you to gain an understanding. Now let's talk about the Lewis acid. So we've talked about the Brewster-Lawrence acid. We said Brewster-Lawrence definition of acid is an acid is a substance that is a proton donor, while a base is a substance that is a proton acceptor. Lewis defined, now let's come to the Lewis definition. Lewis defined an acid as an electron pair acceptor. So acids, according to Lewis definition, accept a pair of what? Electron. So we have it as an electron pair acceptor. Alright? Electron pair acceptor. And a base as an electron pair donor. So any substance that is capable of accepting an electron is an acid, while any substance capable of donating an electron, according to Lewis acid, is a base. Now note the difference. Brewster-Lawrence said acid are proton donor. Lewis said acid are electron acceptor, not electron donor. Not what? Electron donor, because that is what some of you will now say, oh, acid are substances that donate electron. No! Acid are substances that what? That accept electron, according to the Lewis definition. Why base? Substances that what? Donate electron. So it's just like the inverse of the definition of acid and base as postulated by who? By Brewster-Lawrence. Is that okay? So that is that. Now look at this reaction. This reaction between H plus and OH negative to form what? Water. That is this reaction you can see here. The hydrozonium ion, according to Lewis dot structure, has 3 lone pairs of electron. Now this lone pair of electron can actually be donated to H plus via a kind of bonding called dative bond or coordinate covalent bond, where one of the participating group is the one that donates the electron, right? Exactly. So this one will be donating electron to form bond with H plus, which is now what we are going to be having here. Now, because you use one of the electron pair to form bond here, which is this bond you can see here, contain these two electron pair, we are now left with just another two electron pair. Are you getting it? Which contain an electron pair here rather. We are now left with this one that contain two electron pair. This acid and base, hydrogen ion, hydroxide ion to form what? Water. Acid base reaction. Now another acid base reaction is reaction between ammonia and hydrogen ion. Are you getting it? Or a proton. Now ammonia is capable of donating electron to this proton here. This is a proton, call it a proton, which is acting as an acid. Ammonia with its lone pair of electron via what kind of bonding? Dative, can donate to this. Now when it's donating to this, you are going to form something like this. Is that okay? Exactly. Now there will not be a bond between this group and this group here. No lone pair of electron will be remaining, and this is called the ammonium ion. So according to the Lewis definition, any substance that is capable of having excess of electron that it can donate is a base, while any substance that is capable of accepting that electron is an acid. So acid accepts electron, acids accept electron, they accept electron, while base donates electron. Is that okay? Acid accepts electron, while base donates electron. Now let's see another reaction very quickly. This reaction is the reaction between ammonia and boron trifluoride. Now boron trifluoride is a base, it's an acid, is a Lewis acid. Now why do we say boron trifluoride is a Lewis acid? It's electron deficient. That means it does not have electron. Most of the electron deficient compounds or molecules are Lewis acid because they are capable of what? Accepting proton. When we say electron deficient, it means that when you count the number of electrons around it, it's not complete octet. And boron trifluoride is one good example. Then electron rich, they are electron donor, and they are called what? Lewis base. So you can see ammonia is a base, while boron trifluoride is what? An acid. Now this ammonia is capable of donating electron to this base to form an ammonium boron trifluoride linkage or a base. This is an example of what? Acid base reaction. Is that okay? Let me explain it to you guys here. It's very easy. Now you have something like this. Boron trifluoride. Boron trifluoride, the Lewis dot structure, something like this, plus ammonia, the Lewis dot structure for ammonia, something like this. Now this boron trifluoride, if you count, you discover that it's having these two electron, making it a total of what? 6. Because if you guys were following in year 1, we are told that for every bond is 2 electrons. So you have 2 electrons, 6. A total of how many electrons are they supposed to have? 8 electrons. Is that okay? So that at the end of the day, because the 8th electron is not complete, you call this compound boron trifluoride as electron deficient species. So this group here, which is ammonia, is electron, it has excess of electrons, so you call it a base, electron rich, and is capable of donating this electron to form bond with this boron trifluoride. So that at the end of the day, what are you now going to form? You're now going to form a bond between boron trifluoride, and ammonia. Now the reaction is now balanced. If you count around boron, you have 1, 2, 3, 4 bonds. If you count around nitrogen, you have 1, 2, 3, 4, which is 8 electrons in their outermost shell. Now, most Lewis acids are used in catalysts for aromatic substitution reaction, and they include, of course, you've seen boron trifluoride. Aluminium trichloride is also a Lewis acid. So you may be asked to give examples of Lewis acid. Aluminium trichloride is one of them. Are you getting it? Then boron trifluoride is one of them. Most positive charge ion are Lewis acid. Most positive charged ions are Lewis acid. Is that okay? So all these are examples of Lewis acid that are used for most reactions. I told you that aluminum trichloride is used as a catalyst for aromatic substitution reaction, which I believe you have done before, for aromatic substitution reaction. It is used as